Welcome back. In the previous video, we have learned what is meant by the equivalent the noise temperature for a noisy RF and microwave circuit. And we said that the equivalent noise temperature is, I'm going to replace the RF circuit by an equivalent resistance, and this resistance will equal or will be matched to the load resistance, and this resistance would have an equivalent temperature Te, such that the output noise of this temperature or the output noise of this equivalent resistor, it would be K multiplied by Te multiplied by the bandwidth, which is the same as the noise from the actual circuit. And we studied also how to measure this equivalent noise temperature. Now we are going to introduce another measure for the noise in microwave circuits, which is called a noise figure, and we are going to relate this noise figure to the noise temperature. Effectively, if we have any two-port network, we have an input and an output. So if the input is connected to a noise source, so we have a certain value for the input signal and certain value for the input noise level. Then both the signal and the noise of the input will pass through the two-port network. For example, this two-port network, an amplifier or filter. In this case, the output signal will be proportional to the input signal. However, the output noise will be proportional to the input noise plus the internal noise of this circuit. So in this case, the signal to noise ratio at the input, it would be greater than the signal to noise ratio at the output, because I have increased the output signal by a certain amplification factor, but I have increased the noise, but this is the same amplification factor in addition to the internal noise. So the output noise is greater than just the amplification of the internal noise. So the input signal to noise ratio is usually greater than the output signal to noise ratio. We are going to define the noise figure as the ratio between the signal to noise at the input to the signal to the noise at the output. This is actually the definition of the noise figure. So we say that the noise figure of a component is a measure of the degradation in the signal to noise ratio between the input and the output of this component. The signal to noise ratio is the ratio of the desired signal power to the undesired noise power. And so the signal to noise ratio is dependent on the signal power, because effectively it is the signal power to the undesired signal noise power. So it depends on the signal power. When noise and desired signal are applied to the input of a noiseless network, both the noise and signal will be attenuated or amplified by the same factor. So the signal to noise ratio at the input will be the signal to noise ratio at the output, so that the signal to noise ratio will be unchanged. However, if the network is noisy, the output noise power will be increased more than the output signal power. Why? Because the output noise power will be amplified by the factor G of the network. In addition, we will add the internal noise. So the output noise power will be increased more than the output signal power. So in this case, the signal to noise ratio at the output would be less than the signal to noise ratio at the input, so that the output signal to noise ratio will be reduced. Here we have an example of a noisy network, with equivalent temperature or equivalent noise temperature TE and gain G and bandwidth B. And this noise network is connected to a noise source. And we are going to assume that this noise source is set down at the ambient temperature T naught or the room temperature, which equal 290 Kelvin. In this case, the total input power to the noise network would be the input signal plus the input noise. So the total input power would be the input signal plus the input noise. The total output power in this case would be the output signal plus the output noise. As I said, we are going to define the noise figure F as the signal to noise ratio at the input to the signal to noise ratio at the output. And once again, the output noise here is the amplification of the input noise here plus the internal noise in the network. So the signal to noise ratio at the output is less than the signal to noise ratio at the input. So in this case, the noise figure is always greater than or equal unity. It would be unity if the network is noiseless. There is no noise in the network, so in this case, this ratio would be unity. But for any noisy network, the noise figure is greater than 1. It should be noted that the definition of the noise figure is based on the room temperature only. So, by definition, the input noise power is assumed to be the noise power resulting for matched resistor at the room temperature T naught equal 290 Kelvin. And take care, the definition of the noise figure is based on the input is matched to the network and is in the room temperature at 290 Kelvin. So in this case, the input noise or the power of the input noise Ni will be K multiplied by T naught, which is 290 Kelvin, multiplied by the operating bandwidth of the network. Now to calculate the noise figure, we say that okay, we have an input signal Si, which is the power of the input signal, and input noise Ni, which is Kt naught B, and we agreed that T naught is 290 kelvins. On the other hand, or in the other port, the output signal will be the amplification of the input signal. So its output will be the gain of the amplifier multiplied by the input signal Si. But the output noise, it would be the amplification of the input noise, which is gain G multiplied by K multiplied by T naught multiplied by D, plus the internal noise due to the equivalent noise temperature TE. So it would be plus K multiplied by G multiplied by D multiplied by the equivalent noise temperature TE. By taking K, G, B as a common factor, the output noise, it would be KGB multiplied by T naught plus the equivalent noise temperature for this noise unit. Now, by applying the definition of the input signal and the input noise and the output signal and the output noise, we can calculate the noise figure F as the input signal over the input noise. The input signal is Si, the input noise is K T naught B, over S naught, the output signal G multiplied by Si, 1 over 1 over n naught, it would be n naught in the numerator. The output noise, it would be k multiplied by g multiplied by d multiplied by t naught plus t. Now, by eliminating si with si, g with g, k and b with k and b, the remaining, it would be simply t naught plus te over t naught. By dividing by t naught, it would be 1 plus te over t naught, or in other words, 1 plus the equivalent noise temperature of the noisy network over the room temperature T naught. And it should be noted that because this is noisy network, it will have a noise temperature. So the value of Te over T naught is greater than 0. So 1 plus something, it will be greater than unity. So as I said, the noise figure is always greater than unity. If we calculate the noise figure in dB, it would be 10 log this value. So in dB, the noise figure, it would be 10 log multiply 10 log of 1 plus Te over T naught in dB. And because this is greater than unity, the noise figure in dB, it would be greater than 0 dB. So the optimum noise figure is 0 dB, or as a ratio it would be unity. This means that the network is lossless, or the network is noiseless. There is no noise in the network. But for practical networks, the noise figure is always greater than unity, and in dB is always greater than 0 dB. Okay. So, as I said here, this is the noise figure, 1 plus Te over T naught greater than unity. So, if I know the noise figure, I can obtain the equivalent noise temperature of the noisy network. By solving this equation, we can say that, okay, if f equal 1 plus Te over T naught, we can say that, okay, Te will be f minus 1 multiplied by T naught. So the effective or the equivalent noise temperature for a noisy network is obtained from the noise figure as the noise figure minus 1 multiplied by the room temperature 290 kelvins. If the noise figure of the circuit is unity, this means that the equivalent noise temperature of this circuit will be 0. This means that this circuit is noiseless. Okay? That's what we are seeing here. If the network were noiseless, the equivalent temperature, it would be 0, and the noise figure, it would be unity, or in terms of dB, it would be 0 dB. Effectively, the noise figure and equivalent noise temperature are the two sides of the same coin. So we can say that noise figure is defined for a matched input source, and for a noise source equivalent to matched load at the temperature T naught equal 290 kelvins. Noise figure and equivalent noise temperature F and Te are interchangeable characterization of the noise properties of the component. So if I know the noise figure, I can obtain the equivalent noise temperature, such that the equivalent noise temperature, it would be the noise figure minus 1 multiplied by T naught, where T naught is 290 kelvins. On the other hand, if I have the equivalent noise temperature, I can obtain the noise figure. As the noise figure, it will be 1 plus the equivalent noise temperature over T naught. So as I said, noise figure and equivalent temperature are two sides of the same coin to define the noise of the noisy circuit. For the case of a lossy two-port network, In the case of lossy two-port network, it would be the opposite for the amplifier. Instead of obtaining gain, we have losses. So assume that I have a lossy transmission line section with total loss L and noise temperature T and characteristic impedance Z naught equals R. So the total output noise for such transmission line section is actually K multiplied by the noise temperature T multiplied by the operating bandwidth. To obtain the noise figure for such lossy two-port network, we are going to assume that, okay, we are going to connect this lossy network by a matched load with the same characteristic impedance R, and because of the thermal stability of all the problem, effectively the noise temperature of this resistor, it would be T, not T naught. So in this case, the total system will be at equilibrium, has the same equivalent noise temperature T. And the output noise in this case, as I said, it would be KT multiplied by D, which can be divided into two parts. The internal noise inside this transmission line network, or this lossy two-port network, plus the noise coming from the input port. So we say that for the case of lossy two-port network, the power gain for lossy network is less than unity. So instead of talking about gain, we are talking about the loss factor. And we are going to define the loss factor L as the reciprocal of the gain. And as I said, the gain here is less than unity, so the loss factor 1 over G is greater than unity. So we are going to define everything in terms of the loss factor instead of the gain. Alright? Now, we say that the total output noise is KTB, which can be represented as the summation of two noise parts. The gain multiplied by KTB, which is the internal noise of this lossy two-port network, plus the noise which has been added from the matched load at the other term, or the other terminal. So G multiplied by the added noise. The added noise here is the noise from the terminating resistance here R, which is also at the same temperature as the equilibrium. So the added noise here, in terms of the total output noise, can be obtained by taking this term to the other side here. So we have KTB minus JKTB. So it would be simply 1 minus J multiplied by KTB. And then by dividing it by J, we can obtain the added noise due to, the added noise due to the matched load at the other term. So the added noise, it would be 1 minus J multiplied by KTB over J, which is effectively, it can be represented 1 over J minus 1. 1 over J is the loss factor. So it can be represented as the loss factor minus 1 multiplied by KTB. So the added noise due to the terminating matched load at the equilibrium temperature of the noise temperature, it would be the loss factor minus 1 multiplied by the value of the noise output noise KT. From this, we can say that, okay, according to the definition of the equivalent temperature, we can say that the equivalent noise temperature in this case, it would be 1 minus J over J multiplied by the temperature T. Because here, this would be the noise due to the lossy two-port network here would be 1 minus J over J multiplied by T. Or in other words, the equivalent noise temperature of this two-port network in this case would be simply the loss factor minus 1 multiplied by the equilibrium temperature T. So, the equivalent noise temperature for the lossy two-port network, it would be the loss factor minus 1 multiplied by the equilibrium temperature for the lossy two-port network connected with a matched load with the same temperature T. From this, we said that, okay, the equivalent noise temperature, it would be the loss factor minus 1 multiplied by the equilibrium temperature T. On the other hand, we have defined that the noise figure F is 1 plus the equivalent noise temperature over T naught. So, by using the definition for what we have obtained for the equivalent noise temperature, so it would be L minus 1 multiplied by T over T naught. So, the noise figure of the lossy two-port network would be 1 plus L minus 1 multiplied by the equilibrium temperature of the network T over the room temperature T naught. If the equilibrium temperature of this two-port network is the room temperature itself, so in this case, if we are using this lossy network at the room temperature T, it would be T naught. So in this case, the noise figure would be 1 plus L minus 1. Or in other words, the noise figure, it would be simply the attenuation factor or the loss factor L. So for any two-port, for any lossy two-port network, the noise figure of the lossy two-port network at the room temperature is simply the attenuation of this lossy two-port network. So assume that we have a 6 dB attenuator at room temperature. This means that the noise figure of this 6 dB attenuator is 6 dB. So the noise figure in this case, or the noise factor, the noise figure would be directly the same value of the attenuation. Because F here equal the attenuation factor, or the loss factor. Okay? The question now, what will be the situation if we have cascaded networks? For example, if I'm talking about a receiver, at the beginning I have a band pass filter, then I have a low noise amplifier, then I have a mixer. So all of these components or circuits are in cascaded form. So what will be the total noise figure for a cascaded system? This is what we are going to see in the following picture.